Okay, so let's get started. So you may recall that we're finished with the chapter on gases, which was chapter 13. So we're going to start now with chapter 11. If you remember, we did chapter 10, and then we skipped the chapter 13. Chapter 10 dealt with heat and energy and all that good stuff. Chapter 13 deals with gases. So what we're going to do now is jump back to chapter 11. And as you can see on the screen, it's dealing with the modern atomic theory and the periodic table. And this is where we're going to see how the structure of the atoms, in particular with respect to the arrangement of the electrons, how that is related to the position of the particular elements in the periodic table. So just to give you a brief outline of how we come to a current understanding of the nature of the atom, the first people who were on record to suggest that matter is made up of a very small, minute particles were the Greeks. In fact, if I'm not mistaken, I think it was Aristotle who came up with this notion that you can actually break down substances until you get to the smallest unit. And he came up with a word from which we have our modern word atoms. The word he came up with was, let me get my pen here. The word he came up with was atomos, A-T-O-M-O-S, to describe these particles. And it is from that term that we have our current English word of atoms. And of course, when somebody in science comes up with an idea like this, then you have scientists who try to test the idea to see if there's any truth to it. So you have early chemists who perform experiments, which led to information which Dalton used to come up with his theory, atomic theory. And I think we talked about it before, but basically his theory talks about the fact that all matter is made up of small particles that are indivisible, which we now know not to be true. He also talked about the fact that whenever you have a chemical, well, before I get to that, he talked about the fact that atoms of the same element will be identical in every way. So if you look at two oxygen atoms, you won't be able to tell the difference between them. But what you'll find is that atoms of different elements will be different. And for example, if you look at a hydrogen atom and compare it to a sodium atom, you'll see that they will be different in several respects, mass, size, etc. Then limitations to Dalton's models were found, and that led to experiments that were done by these two guys, Thomson and Rutherford, and they came up with different models of the atom. And even after that, there were some issues with those theories as well. So other people did more theoretical work, and that led to the current understanding of the nature of the atom. Now, for those of you who plan to do Chem 1, you're going to get into these discussions in a bit more detail. What I've just given you is just basically a very broad overview of how we arrive at the modern understanding of atoms and their nature, all right? So in order for us to have some understanding, we need to talk about electromagnetic radiation, right? And this might seem a bit unrelated, but it's actually related, as you're going to see later on. Okay, so let's talk about electromagnetic radiation. It's a form of energy. And if I remember correctly, when I was doing physics back in high school, we learned that there are three ways that energy can be transmitted: through conduction, convection, and radiation. The thing about conduction and convection is that they require a material medium, all right? So for example, if you want to conduct heat through a metal, then of course you need a metal material in order for the heat energy to transfer from one point of the metal to the other. The same is true for convection. On the other hand, in the case of electromagnetic radiation, one can transfer energy through vacuum or through space, all right? So it has to do with the nature of this form of energy transfer, so to speak. And as you can see here, in the name, it says electromagnetic radiation. And what this implies is that this sort of energy transfer requires oscillating electric and magnetic fields, all right? Now, to simplify things a bit, what we can say is that the oscillating electric and magnetic fields can be represented by a waveform. So therefore, we have to understand the nature of a waveform in order for us to understand certain aspects of electromagnetic radiation. Now, before we get to the waveform discussion, you need to understand that there are different types of electromagnetic radiation. And these are listed right here. You have, for example, the light from the sun. You have X-rays, microwaves, radio waves, television waves, and radiant heat. And they all have one thing in common, and that is, as I said before, they show wave-like behavior, all right? So they behave like a wave. Another thing that they have in common is that they all travel at the same speed in a vacuum. And that speed is given as 3.00 times 10 to the 8 meters per second when expressed to three significant figures, right? So all forms of electromagnetic radiation will travel at this speed. Doesn't matter if it's X-rays, microwaves, radio waves, whatever, right? They all travel at this speed, all right? Okay, so as I said before, we need to understand the nature and characteristic of a wave in order for us to understand how electromagnetic radiation behaves. So there are basically two, actually there are three, but we'll be focused on two particular characteristics of any waveform. One is known as the wavelength, which is represented by this symbol here. It's a Greek letter known as lambda. It looks like an upside down Y, all right? So that's the symbol that is used universally for the wavelength. And by definition, the wavelength is basically the distance between two successive peaks. As you can see in this waveform here, the distance from this peak to this peak is defined as a wavelength, or we can define it as the distance between two successive troughs, like from here to here, right? And they will give the same value for a typical wave, all right? So that's a definition of the wavelength. It's basically the distance between two successive peaks or two successive troughs, all right? So that's the wavelength. That's one important feature of a waveform. Another important feature is known as the frequency. And as you can see here, it's represented by this Greek symbol. Now it looks like a V, but it's actually the Greek letter nu. And I will also say that in some textbooks, they simply use the letter F to represent the frequency. So you can use the letter F, or you can use this symbol, which is nu, to represent the frequency. Now, what is the frequency of the wave? The frequency of a waveform is the number of wavelengths that pass a particular point per second. So if you focus on one point here and the wave is moving, the number of wavelengths that passes that point in a second is called the frequency. So that's a wave moving. And if you count the number of waveforms, or the number of wavelengths, I should say, that passes that particular point per second, then that is the frequency. Now, I neglected to mention earlier that as far as the wavelength is concerned, let me go back to this here. As far as the wavelength is concerned, the wavelength, let me get my pen out here. The wavelength can be expressed in any unit. The most common unit, I would say, would be the meter unit, but you can also have it expressed in other units like nanometer, micrometer, even kilometers in some cases. It all depends on the type of radiation that you're dealing with. So these are the common units. The meter unit is the most common, to be perfectly honest. So you'll see this more often, but you can also have the wavelength expressed in other units of length. Now, as far as the frequency is concerned, because of the definition here, which is the number of wavelength that passes a particular point per second, the unit of frequency is seconds to the minus 1. So I'm writing this down here. So the unit of frequency is seconds to the minus 1. And there's a special name given to this unit. It's called the Hertz unit, right? H-E-R-T-Z, all right? Or symbolized Hz. So if you see the symbol here, you should understand it's the same thing as seconds to the minus 1, all right? Okay, so that's a unit of frequency. And then we get to another characteristic of a waveform, and that's the speed. And the speed is actually related to the frequency and the wavelength, and it is given by this formula here. The speed, well, let me just say firstly what the speed is. The speed is basically how fast a wave moves through space. And as you can see here in this formula here, back to my pointer, the speed of a wave will be equal to the wavelength times the frequency, all right? Now, if the wavelength is in meters, and the frequency is in seconds to the -1, that means that the units of wavelength is meters second to the -1, which is the same thing as meters per second, all right? So that's the relationship between the wavelength, the frequency, and the speed of a wave, all right? Okay, so that's basically the three characteristics that you need to know about a wave. And there's actually a fourth characteristic, which we won't get into. It has to do with the amplitude, which is related to the intensity of the particular radiation, but we won't get into that. So let's talk about another aspect of radiation. And it turns out, and I won't go into the story, there's a long story behind this in terms of the work that scientists did, but it turns out that light and other forms of radiation behave not only as a waveform, but also behave as a stream of particles. And these light particles are called photons, all right? So basically, we have two models to represent the different forms of radiation. We have what is known as a wave model, which basically says that radiation acts as a waveform, and we talked about the different characteristics of the waveform. And then we have what is known as the particle model, which basically says that the radiation behaves as if it's a stream of particles, and these particles are called photons, all right? And these might seem contradictory, but it just simply turns out that one can explain some aspects of radiation using the wave model and other aspects using the particle model. Okay, so let's talk about what we call the electromagnetic spectrum. The electromagnetic spectrum is basically a list of the different forms of radiation in terms of their increasing frequency or increasing wavelength. Now, let me just say this. Remember I said, let me rewrite the equation up here. Remember I said that the frequency, the speed of a wave, V is equal to the wavelength multiplied by the frequency, all right? Now, in the case of electromagnetic radiation, the wavelength, or I should say the velocity, is the same. I made that point before. I said it doesn't matter what type of radiation it is, as long as it is electromagnetic radiation, it has the same speed, and that speed is equal to 3.00 times 10 to the 8 meters per second. So therefore, we tend to, in chemistry and physics, use the letter C to represent the speed of electromagnetic radiation. So that is equal to 3.00 times 10 to the 8 meters per second. So therefore, we can replace the V with the C equals to all this here. Now, because of that relationship, one can see that there's an inverse relationship between the wavelength and the frequency. If this is constant, right, that doesn't change for the different forms of radiation. That means that as lambda increases, the wavelength, the frequency decreases, right? So this is for lambda, and that is for nu, the frequency. And of course, the opposite is true. As lambda decreases, then the frequency increases, all right? So that's important so that you understand that there's a relationship between the wavelength of a radiation and the frequency. Now, what you're seeing here on the screen is basically a list of all forms of radiation in order of increasing wavelength, right? So down here, we have what are known as the gamma rays. They have the smallest wavelength of all the forms of radiation that we have listed here, followed by X-rays, right? Followed by ultraviolet rays. And then we have a narrow band here, which basically is consisting of the different colors of light that our eyes are sensitive to. So we're talking about starting with violet, then indigo, then, well, let me just use, there's a memory tool that I use to remember the order of the colors, and that is Roygbiv, Orygbbiv, oops. Right, so that's violet, indigo, blue, green, yellow, orange, and red, all right? So that's what I use to remember the order of the colors. So the way it's ordered here is in the opposite direction to what I have up here, right? So this is basically the narrow band that is a part of the spectrum that our eyes are able to detect, all right? We are not able to see any other form of radiation outside of that narrow band. So as far as this band is concerned, what you'll see is that the red light will have a higher or longer wavelength. So let me put here longer lambda value, and the violet light would have a shorter lambda value, all right? So basically the wavelength increases going this way or going, if you're using this, going this way, all right? And I just want to say that I read somewhere that only in the human species, only the females can tell the difference between indigo and violet. And I certainly believe that to be true because I cannot tell the difference between those two, but I've been told that, or I've been informed that women can tell the difference between those two. Okay, then just beyond the visible range, then you have what is known as the infrared type of radiation, followed by microwave, and then you have the higher wavelength radio waves above, all right? So that's basically the electromagnetic spectrum in a nutshell. Let me just say that because the wavelength increases this way, that means that the frequency would increase in the other direction, all right? Again, because of the inverse relationship between the wavelength and frequency that is given by this equation right here, all right? So that's basically the electromagnetic spectrum. So let's talk about the Bohr atom, and we're going to see the relationship between the atom, the structure of the atom as put forward by Bohr and the electromagnetic spectrum. Now, let's talk about the difference between what is known as the continuous spectrum and later on the line spectrum. Now, if you take white light, for example, light coming from a lamp or coming from the sun, and you pass it through a prism, then what will happen is that that light will be split up into its components, which would be different colors of light as seen in this diagram right here. So here we have the white light source. Get back to my pointer here. Okay, so here we have the white light source, and then that shines through a slit, so that produces a beam, and that beam is allowed to pass through this prism. Now, this prism can be made up of either glass or plastic, but it will be something transparent. And what's going to happen is that as the white light passes through, the different colors of light will undergo what is called refraction. Now, if you have done physics or if you plan to do physics, you know that basically what is happening is that when a light beam is passing from, let's say, vacuum into a medium like glass or prism, or a plastic prism, I should say, then what will happen is that the light would undergo a bending as a result of a reduction in the speed of light as it passes from the vacuum into that medium. And the greater the extent of bending would be, the slower would be the speed of the light as it passes through the medium. So in this particular case, what will happen is that the blue, or I should say the violet light, will undergo the bending most drastically, while the red light will bend, but not bend as much as in the case of the violet light. And the different colors of light will bend again to certain extents. As a result of that, there will be a separation of the lights of different colors. And then by the time it emerges from the other end of the prism and projected onto a screen, you end up with the visible part of the electromagnetic spectrum. So down here you'll have the indigo, the violet, then indigo, which runs into the blue, which runs into the green, which runs into the orange, and then, well, which runs into the yellow, then orange, and then red at the other end, all right? So that's basically what you would observe in the case of the continuous spectrum. And the reason why this is called the continuous spectrum is because as you go from one color to the next, there's no clear line of demarcation between the different colors. So for example, if I were to start from green here, it's very hard to say where the green converts or changes to the yellow. So there's a sort of a gradual changeover as you go from green to yellow, and then from yellow to orange, and then from orange to red, all right? So that's basically what the continuous spectrum is. And this is something that you see, for example, in the rainbow, right? So after rain falls, or if there's moisture in the air, it's the same thing that happens. In that case, it's the sunlight that is undergoing refraction, and the different colors will be separated, and you end up with a rainbow being formed. And that rainbow is actually the visible part of the spectrum that you'll observe. Okay, so that's the spectrum, the visible part of the spectrum. Now, when it comes to certain gases, certain elements existing as gases under extreme high temperature or voltages, then what you'll find is that light will be emitted by these gases, and these types of light will be of different colors. So what we're going to look at is what happens if we have hydrogen. Let me, or what does it say? When the light is passed through a prism, then you're going to end up with a line spectrum, which is different from the continuous spectrum that we just saw. So just to illustrate this particular fact, let's look at the hydrogen lamp, which consists of a tube which contains hydrogen at a very low pressure. And this is subjected to an electric discharge. So you have your tube, you have two electrodes at one end and the other end down here, which is not shown. And that is connected to an external circuit. You flip the switch, and then what happens is that the hydrogen starts to glow. So if that light is passed through a prism, just like we did before in the case of the ordinary lamp, and then, well, passes first through a slit, then a prism, then projected onto a screen, you're going to end up with what is known as a line spectrum. Now, the line spectrum will look like what you see here on the right side of the screen. Now, it might be a bit challenging for you to see the actual lines, but there's one line here which looks like it's purple, and then there's another line here which looks like it's blue, and then there's another line here which looks like a darker blue color, and then there is another line here which is very faint, which looks like a red color. So those are the lines that you'll observe in the case of hydrogen. In fact, I think the next slide shows you a better image. But before we get to that, the point being made here is that unlike the previous spectrum that we saw, which was continuous, this spectrum that we're looking at is discontinuous, because we don't have a continuous change of color as you go from one end to the next. You have large dark gaps between the lines that are formed, all right? So we call this a line spectrum as opposed to a continuous spectrum. So let's see here. Okay, so the point being made here is that the spectrum that is produced by an element like hydrogen or neon or some other element in a gaseous state, which is subjected to an electrical discharge, will not give you all the wavelengths of the visible spectrum, but specific wavelengths as we see here in the case of hydrogen. So this is a better looking representation of the line spectrum of hydrogen. So each line basically is produced as a result of energy that is emitted by an electron of the hydrogen atom when it falls to a lower energy level, and we're going to discuss that later on. So all these lines that you see here that is produced is as a result of electrons jumping from, or falling, I should say, from a higher energy level to a lower energy level. Now, initially, because of the electrical discharge or the heat that is applied, the electron will be promoted to a higher energy level, but that's a very unstable state. So therefore, those electrons will fall back to lower energy levels and basically emit light of a particular wavelength or frequency, which is represented by these lines right here. Okay, so this is basically what is used to support the Bohr model. In fact, the Bohr model is used to explain this observation for hydrogen. So let's go back to, oh, and another important point here is that this sort of line spectra can be produced by other elements, but of course, each element will have its own unique line spectra. So therefore, this is the line spectrum for hydrogen, but for other elements, what you're going to see is that the line spectrum will have a different appearance, different colors lines, and so on and so forth, right? So we can actually use the line spectrum of a particular element to help to identify it. In fact, this is what is used, for example, to identify certain elements in the sun, right? We now know that there are certain elements that exist in the gaseous state up there in the sun, like elements that exist as solids normally down here on Earth exist as gases up there, like iron and other metallic elements. And the reason why we know that is because astronomers have special instruments that they can use to look at the line spectra of the elements that are present up there, and therefore based on the unique pattern in terms of the line spectrum, you can identify certain elements that are present up there in the sun. Okay, so let's talk about Niels Bohr and his model of the atom, which is based on what we just discussed. So Niels Bohr was a Danish physicist, and he carried out research specific to the hydrogen atom, because what he was interested in is looking at how the line spectrum that is produced by the hydrogen atom can explain how the electrons are arranged in the atom. So according to the Bohr model, based on his research, he suggests that in the atom, you have your nucleus, which contains your protons and electrons, and protons and neutrons, and surrounding the nucleus, you have electrons traveling in well-defined, what we call orbits. In some textbooks, they call this a planetary model because it is similar to how you have the planets that are going around the sun. So that's the idea that Bohr was working with, right? And what Bohr suggests is that the line spectrum that we can see for the hydrogen atom is as a result. Oh, before we even get to that, one thing I should say here, which is very important, which is a point that is being made here, is that the electron that is traveling within an orbit like this has a discrete energy value. So therefore, if it is in this orbit, it has a certain amount of energy. If it is in another orbit, then it has a certain amount of energy, and so on and so forth. So basically, the energy that the electron has is dependent on the orbit that it is basically traveling in around the nucleus. And this orbit is at a fixed distance from the nucleus. Okay, so as I was saying, the Bohr model is used to explain the line spectrum that is observed in the case of hydrogen. So how does this explain it? Well, according to the Bohr model, when an electron falls from a higher energy level to a lower energy level, a quantum of energy, which basically means a particle of energy in the form of light, is emitted by the atom. And the color of the light emitted corresponds to one of the lines of the hydrogen spectrum. So basically what the Bohr model is saying is that when the electron is falling from an orbit of a higher energy to a lower energy, then it will emit a certain amount of energy, which is equal to the difference in the energies of the different orbits. And that energy value can be represented by the color of the light, which corresponds to a particular frequency, which corresponds to a certain amount of energy associated with that light or with that line, all right? So that's basically the Bohr model. So for example, let's say that the electron, according to the Bohr model, is in the third orbit away from the nucleus. And let's say it falls from the third orbit. Okay, why is this not budging? Sorry about this. Okay, so let's say it falls from the third orbit to the second orbit. Then that corresponds to the red line that is produced in the line spectrum, because the energy gap between those two orbits is equal to the energy of the radiation, which corresponds to the red line, all right? So that's basically how the Bohr model explains that line. Let's say, let's say instead of falling to the second orbit, let's say that the electron, which is in the third orbit from the nucleus, falls from the third orbit to the first orbit, which is the one closest to the nucleus. Then that corresponds to the formation of the green line, because basically, according to the Bohr model, the energy gap between the third orbit and the first orbit here will be equal to the energy that is produced when the green light is produced as a result of that transition. All right, so that's basically how the Bohr model works. And in fact, for those of you who plan to do Chem 1, what you'll find is that you can actually do calculations which shows you how to calculate the energy difference between the orbits, and you can actually calculate also the frequency of the radiation that is produced. All right, so that's basically how the Bohr model works. Now, let me move on now to a definition here. Basically, what the point being made here is that the light that is emitted is not emitted continuously. It is emitted in discrete packets known as quanta, which is basically the same thing as the photons that we talked about. So going back to where the light is produced as a result of the transition from the third to the second orbit, then basically that energy gap is corresponding to this quanta of energy or radiation that is produced. All right, so that's basically what the Bohr model is suggesting, and that basically explains the different colors of light or lines in the line spectrum for the hydrogen atom. All right, okay, an electron can have several possible energies depending on the orbit. So the electron can be here, or here, or here, right? Now this here, where the electron is closest to the nucleus, that's the most stable state. However, you can have the electron being in the other orbits, which means that the electron would have to gain energy in order to be promoted from the lower orbit to the higher orbit. But as I said before, that would be a very stable arrangement, and therefore, as a result, the electron will fall back to the lower orbit, producing radiation of a particular frequency or color of light, and therefore that would appear as a particular line in the spectrum for the hydrogen atom. All right. Now, some general statements here concerning the Bohr model. It turns out that Bohr's calculations succeeded very well when it comes to predicting or explaining what was observed in terms of the hydrogen spectrum, the spectral lines. So the Bohr model works well for the hydrogen atom. However, it turns out that this method, the Bohr model, does not succeed for the heavier atoms. So even for the atom which comes after hydrogen, namely helium, the Bohr model doesn't work for that, right? And doesn't work for any other atom after helium, okay? And the main reason for that is that by virtue of the fact that you have other electrons present, that tends to complicate things a bit, because not only do you have the electrons transitioning from one orbit to the other in relation to the nucleus, but you have electrons interacting with each other, you have repulsive forces, and that kind of distorts what the Bohr model would predict. So that's a limitation of the Bohr model. It works well for hydrogen, but it does not work well for other heavier atoms. So therefore, as a result, more theoretical work was done in order to gain a better understanding of how the electrons are arranged in the atom. So this brings us now to this guy, and I apologize to anybody in the class who speaks French because I'm about to destroy this guy's name. But this guy's name is Louis de Broglie, and he suggested that since all waveforms have some particle properties, then all moving objects will have wave properties, all right? So basically what he's saying is that because of the particle wave, what we call duality of radiation, where we can represent the way radiation, how should I put this? We can explain the behavior of radiation as either wave-like properties or particle properties. Then basically any object that is moving, doesn't matter what it is, can have wave properties. That's basically what de Broglie says. And there's an equation that he came up with, which we won't get into, but for those of you who plan to do Chem 1, you're going to meet that equation. Now, based on what de Broglie suggested, what he showed based on the theoretical work that he did was that the wavelength of ordinary sized objects, such as a baseball or, a car or whatever, because of their relatively large mass, the wavelength is too small to be observed. But when it comes to very small particles like electrons, then those wavelengths can be detected. All right. So that's basically what de Broglie came up with. And then another guy, and this is certainly something that we definitely won't get into in detail because it's a very, very complicated, abstract theoretical approach. A guy by the name of Irwin Schrodinger, he came up with a mathematical model. In fact, he came up with an equation, which I won't show you here. I don't want you guys suffering from being exposed to something like this too soon. But basically, just giving you a broad overview of what he did, he created a mathematical theoretical model, which led to a new branch of physics, which is known as wave or quantum mechanics. And based on his calculations, instead of talking about an electron being located within a particular orbit, which is what Bohr suggested, he came up with an approach which talks about the fact that instead of orbits, what you'll find is that electrons will be located in a region around an atom, and that region is called an orbital. So the modern version of how the electrons are arranged in the atom is that they're not arranged in orbits. They are arranged or located within a region of space, and that region of space is called an orbital, all right? So basically, the consequence of his approach is that one cannot locate an electron at a particular time in an atom, all right? The best thing we can do is talk about the region in space where there's a probability, which is very high, above 90%, of finding an electron within that region, right? So as stated here, based on wave mechanics, it is clear that electrons are not revolving around a nucleus in orbits. Instead, they are located in what we call orbitals, which is a region in space around a nucleus where there's a high probability of finding an electron. Okay, so that's basically, as I said before, there's a lot more detail, a lot more math, especially advanced calculus, which is involved in all of this here. But for our purposes, we don't have to go through all that. So that's why I'm just giving you basically an overview of how we arrive at our current understanding of how the electrons are arranged in an atom. Now, before we get to the energy levels of electrons, I want to do a couple of examples going back to the relationship, excuse me, between wavelength frequency and the speed of radiation. So what I'm going to do is see if I can find a couple of questions online. Okay, speed of light. Okay, I'm just going to try to find a couple of examples that we can work so that you, let me see here. Let me see here. Let me try this here. No, this is a physics paper. No, let me get out of this here. Try this one. I'm just trying to find some problems. Okay, this one, oh, I hate when they give answers already. Let me see this one here. Okay, that one. I'm looking for something without any answers. Let me see this here. Okay, here is a couple of questions. Okay, this earphones is really hurting my ears. Okay, so this question, let's deal with this first one here. And let me open up writing. Okay. So let's deal with this question. It says the yellow light given off a sodium lamp has a wavelength of 589 nanometers. What is the frequency of this radiation? Okay, so basically you're given the wavelength, which is 589. Okay, let me do this here. Okay, so the wavelength, lambda, is equal to 589 nanometers, all right? And the question is asking for the frequency, all right? Let me just look at the question again just to be sure. Right, so the question is asking for the frequency. Now remember, the relationship between the speed of light, wavelength, and frequency is C is equal to lambda times nu, which is the frequency. So therefore, nu would be equal to C divided by lambda, all right? Now, C is always going to be 3.00 times 10 to the 8 meters per second. That is the speed of all forms of radiation. And the wavelength is equal to 589 nanometers. However, because we have meters here, we have to convert the nanometer unit here to meters. So therefore, we're going to have 1 nanometer down here. And up here, we're going to have 10 to the minus 9 meters, because that's the relationship between the meter unit and the nanometer unit. So what's going to happen is the nanometer units will cancel out here and here, and the meter units will cancel out here and here, all right? So all we need to do now is our number crunching. So let me do that here. And folks, please work or do this calculation along with me, because I could be doing something totally wrong and you can correct me. So it is 3 times 10 to the 8 divided by 589 times 10 to the minus 9. Okay, I don't know why that happened. Let me do this again. 3 times 10 to the 8 divided by 589 times 10 to the minus 9. And according to my calculations, and the answer will have to be rounded off to 3 sig figs. According to my calculations, this works out to be 5.09 times 10 to the 14. And the units here would be second to the minus 1, or if you want to use Hertz, that's fine as well. But this would be the answer to that first question. All right? Okay, any questions about this particular example? Any questions? Any questions? Okay, let's look at another example. It says here, a laser used to weld detached retinas produces radiation with a frequency of 4.69 times 10 to the 14. What is the wavelength of this radiation? So we're going to use the same equation here, but the wavelength, or I should say the frequency, is given 4.69. Let me write this here. So frequency is equal to 4.69 times 10 to the 14 Hertz. So let me take out all of that. Okay, so the question gives us the frequency, and the question is asking for the wavelength, which in this case would be equal to C divided by the frequency, right? So all we have to do is put the numbers in. 3.00 times 10 to the 8 meters seconds to the minus 1 divided by the frequency, which is 4.69 times 10 to the 14 seconds to the minus 1. So these units will cancel out here and here. So your final answer would be in meters, all right? So let's do that calculation. 3 times 10 to the 8 divided by 4.69 times 10 to the 14. And according to my calculations, this works out to be equal to 6, how many sig figs? 4 sig figs, I mean 3 sig figs. So this will be 6.40 times 10 to the minus 7, all right? So that's basically how that is done, all right? Okay, any questions about this example? Any questions? Any questions? Okay, so I thought it was important for me to show you how to do a couple of examples of this type of problem. And in fact, let me go to your Canvas shell right here. And let me go to the folder for chapter 11. And okay, so let me see here. Let me unpublish that. So basically what I'm going to do is, I'm sorry about this, folks. Let me just go through this quickly. I'm going to publish assignment number 30 for you guys to do, because assignment number 30 basically is based on what I just did, looking at the relationship between wavelength frequency and the speed of radiation. So let me go to assignments here and publish the folder for chapter 11. Okay, so that will be due next week, all right? So please make sure that you do that assignment. Okay, so let's continue our discussion of the energy levels of electrons in an atom. So we talked about orbitals instead of orbits, which is a region in space where a particular electron will be found in an atom, all right? So what we're going to talk about now is the relationship between the energy levels and the orbits. So according to, going back to the Bohr model, basically what the Bohr model suggests is that the energies of the electrons in an atom are quantized. And what that means basically is that the electron energies can only have specific values. So the electron energies cannot be continuous. They have specific value, and therefore when the electron moves from one energy level to another, then the change in energy would be of a fixed value, all right? Now, of course, the wave mechanical model that Schrodinger came up with makes a similar prediction, and it works better because, as we said before, it works not only for hydrogen, but for other atoms. So it turns out that these energy levels that were predicted by the wave mechanical model, it corresponds to the orbits in the Bohr model. So basically, when it comes to the hydrogen atom, we have these energy levels, right? We have the first energy level where n is equal to 1. There's a special name given to these numbers. These are called the principal quantum numbers. So we have the principal quantum number 1 for the lowest energy level. Then we have n equal 2, then n equal 3, and n equal 4. And you have others as well above that. And you'll notice that in terms of the spacing of the energy levels, as you go up in terms of energy, the spacing decreases. So the biggest gap here is between the n equal 2 and n equal 1 energy level. Then you have a smaller gap between n equals 3 and n equal 4. And then you have even a smaller gap between n equal 4 and n equal 3, and so on and so forth as the energy increases, all right? And this is true not only for hydrogen, but true for the other elements themselves. And as stated before, each energy level is given what is known as a principal quantum number, which would be the integers 1, 2, 3, etc. All right? Okay, so within these energy levels, what you'll find is that you have further subdivisions, which are known as sublevels, right? And this is all as a result of the work that was done by Schrodinger when he came up with his model. Now, when it comes to the n equal 1 energy level, there's only one sublevel, and that's called the 1s sublevel, all right? So wherever you have the first energy level, there's only one sublevel there. In the case of the n equal 2 energy level, there are two sublevels. One is called 2s, the other one is called a 2p sublevel. And then when it comes to the n equal 3 sublevel, there are three, when it comes to the n equal 3 energy level, there are three sublevels. You have the 3s, the 3p, and the 3d. And then finally, when you get to the fourth energy level, you have four sublevels. They're called the 4s, 4p, 4d, and 4f. And then you have some other higher ones as well, which we won't get into. So the key thing you need to understand is that within each energy level, you have the different sublevels. And this is how we can make a prediction as to what sublevels are present. In the case of the first sublevel or first energy level, you have only one sublevel. In the case of the second energy level, you have two sublevels, and so on and so forth for the third and the fourth sublevels. Now, you might be wondering, where does the orbitals come into play when it comes to these sublevels? Then here it is. Within each sublevel, you have electrons which are found in their respective orbitals, right? So for the s sublevel, you have what are known as s orbitals, right? And the shape of these s orbitals, as you can see here, is spherical, like a ball, all right? And so that's basically the description of the s orbital. And as we said before, an orbital is a region in space in an atom where there's a high probability, about 90% probability, that the electron will be found in that region. So in the case of the s orbital, which has a spherical shape, the probability of finding the electron there within that spherical shape is 90%, all right? So that's the s orbital that is found within the s sublevel. Now, the thing about atomic orbitals, and this is true not only for s orbitals, but any type of orbital, what you'll find is that they can have a maximum of 2 electrons. You can't have more than 2 electrons occupying the same orbital, all right? Another thing we need to talk about with respect to these electrons occupying the same orbital is that if you have 2 electrons occupying the same orbital, then they must be spinning in different directions, all right? Again, this is a consequence of the Schrodinger approach, which we won't get into. I'm just describing to you the result of that. And normally we use arrows to represent the direction of spin. So one arrow pointing up represents the electron spinning in one direction, and the other arrow pointing down represents the electron spinning in the opposite direction. So in this particular case here, we have the 2 electrons occupying the orbital, and they must be spinning in opposite directions. And this is known as the Pauli exclusion principle, which you really don't need to know at this level, but for those of you who plan to do Chem 1, you're going to encounter that discussion as well. So in this particular s orbital, you have 1 electron spinning in one direction and the other electron spinning in the opposite direction, and they're represented by these arrows pointing in opposite directions. Okay, so that is basically the situation for the s orbital. Then when it comes to the p sublevel, it turns out that at the p sublevel, there are 3 orbitals, right? So they are called p orbitals. And they have a particular unique orientation aspect about them. As you can see here, the p orbitals are arranged such that their axis is aligned with the axes of the 3-dimensional Cartesian system, which I'm quite sure you're familiar with from your previous math experience. So we have the x-axis, the y-axis, and the z-axis, which are at mutual right angles, right? So we have this p orbital here aligned along the x-axis. We have this py orbital aligned along the y-axis. And finally, we have the pz orbital here aligned along the z-axis, right? So this is basically how the orbitals of the p sublevel are arranged in 3-dimensional space. Now, one difference between the p orbitals and the s orbitals that we saw before is that the p orbitals are made up of 2 lobes. In some textbooks, they call the shape of the p orbital a dumbbell shape, right? Which is different from what we saw in the case of the s orbital, because as we said before, the s orbitals has a spherical shape, all right? So this is basically a p orbital made up of 2 lobes, another p orbital here, and the third p orbital here. And as I said before, they are aligned along the different axes in the 3-dimensional Cartesian system, all right? Just as in the case of s orbitals, however, p orbitals by themselves, each of them can hold a maximum of 2 electrons, all right? So in the case of the p sublevel where you have 3 p orbitals, the p sublevel can hold a maximum of 6 electrons as a result, right? So again, the electrons will be distributed among these p orbitals such that they're spinning in opposite directions and they share the same p orbital. Now, what you're looking at here are basically the same 3 p orbitals, but how they are actually arranged within the atom, right? Or within a particular sublevel. And as you can see, the p orbitals share common center. You have this p orbital along the y-axis, this p orbital aligned along the x-axis, and this p orbital aligned along the z-axis, all right? So the p orbitals are basically pointing in different directions. So this p orbital is called the px orbital. This p orbital here is called the py orbital. And then finally, this p orbital here is called the pz orbital. And then we have the d sublevel, and it's even more complicated compared to the p sublevel. And in the case of the d sublevel, you have 5 orbitals, and these are basically what they look like. And to be perfectly honest, you don't need to memorize what they look like or how they're oriented, but you need to know that they exist, and this is what they look like, all right? So those are the d orbitals that occur in the d sublevel. And as you can see, they point in different directions. And again, as in the case of the s and p orbitals, each d orbital can have a maximum of 2 electrons. So therefore, at the d sublevel, the maximum number of electrons that will occupy the d sublevel will be 10, 5 times 2, which gives you 10 electrons. And then we have the f sublevel, which I won't even get into, but just to summarize a bit, let me go back. I'm sorry, let me go back here. So just to summarize a bit, as far as the s sublevel is concerned, in the first energy level, or in some textbooks they call it the first shell, you have the s orbital, the 1s orbital, and it has a spherical shape, as you can see here. And then when you get to the second energy level, you have the 2s orbital, which is also spherical in shape. But you also have, in addition, the 2p sublevel, which contains the 2p orbitals, which we discussed earlier. Then we get to the third energy level, or third shell. You have your 3s orbital, which is spherical. You have your 3p orbitals, which are, as we saw before. And then you have your 3d orbitals, or 3d subshell, which contains the d orbitals, which we talked about earlier, all right? And then we get to the fourth energy level, which contains the 4s orbital, the 4p orbitals, the 4d orbitals, which we talk about, and then we have the 4f orbitals, which I won't even show you because their shapes and arrangements are even more complicated. But you need to recognize that in the case of the 4f sublevel, there are 7 orbitals. So let me put here, you have a total of 7 orbitals in the 4f sublevels, all right? So basically that's what happens in terms of how the orbitals are arranged within any atom. All right, so let me get out of this here, go back to my pointer. All right, so this is basically a summary of what we just discussed here in terms of the number of different types of orbitals that exist within each shell and subshell. So just to recap, in the n equal 1 shell, you have only 1 orbital, and that's the 1s orbital. In the n equal 2 shell, or energy level, we have 2 subshells. You have 2 s orbitals within the s subshell here, 2s subshell here, and 3 2p orbitals in the 2p subshell. For n equal 3, you have 3 subshells. You have the 3s subshell, which contains 1 3s orbital. You have the 3p subshell, which contains 3 3p orbitals. And then you have the 3d subshell, which contains the 5 3d orbitals. And then here, in the case of the n equal 4 shell, you have the 4s subshell, only one of them here. You have 3 4p subshells, or 4p orbitals in the 4p subshell. And here we have 5 4d orbitals in the 4d subshell. And then finally here we have the 7 4f orbitals in the 4f subshells. All right, so that's basically a summary of how the subshells are distributed among the different orbitals and the different number of orbitals present within each subshell. Okay, now let's say a few words about the hydrogen atom in terms of the electron arrangement. So first thing we're going to say here is that the most stable arrangement as far as the hydrogen atom is concerned is where the electron, remember there's only 1 electron in the hydrogen atom, and that electron will just simply find itself in the lowest energy orbital, which would be the 1s orbital. That's the most stable state, and we call that stable state the ground state. So whenever you see the term ground state, that means the most stable state. Let me write that down here so that I can more better make that point. So the ground state, let me circle the term or the expression, the ground state is the most stable state. Whenever you see that term, that's what it means. All right. Okay. And then later on, we're going to learn about the excited state, which is not the ground state. So in the case of the hydrogen atom, the ground state of the electron in that atom would be in the 1s orbital, all right? And then what can happen is that the hydrogen atom can absorb energy, and that energy would be used by the electrons to be promoted to higher states or higher energy orbitals. So we call those states which are not the ground state, we call them the excited state. So if the electron is promoted from n equal 1 to n equal 2, then the electron in the n equal 2 shell or energy level is said to be in an excited state, all right? Okay, some other things about the hydrogen, just some general information here. The diameter of the hydrogen nucleus is, is 10 to the minus 13 centimeters about, all right? Whereas the diameter of the electron cloud is 10 to the minus 8 centimeters. So that gives you some ideas to the relative size of the nucleus compared to the rest of the atom. In fact, what you'll notice here is that the diameter of the hydrogen electron cloud, which is basically the diameter of the atom, is 100,000 times greater than the diameter of the nucleus. So that gives you a picture of as to the relative size of the nucleus compared to the atom itself. Hold on, what did I do here? Okay, so that's just some general information concerning the hydrogen atom. Okay, so what we're going to look at now, and I think this is the last thing we're going to discuss in this chapter. Well, actually, for today, I don't think we'll be finished with this chapter yet. We're going to talk about the atomic structure of the first 18 elements of the periodic table, right? So basically, we're going to start with hydrogen and end with argon. And what we're going to look at is basically how the electrons are arranged in these orbitals in these particular elements, all right? Now, in order for us to understand that, there are certain guidelines that we have to follow in order to determine how the electrons will be distributed, right? So the first thing we're going to discuss here, first guideline here, is something that we met before, we talked about before. And the fact is that in any particular orbital, it can have no more than 2 electrons present. And those electrons must be spinning in opposite directions, right? So if you have an s orbital, then you must have a maximum of, you can have a maximum of 2 electrons and no more, all right? And that is true also for any other orbital. The other thing that you need to recognize is that in the ground state, the electrons will occupy the lowest energy orbitals available, and then they will enter a higher energy orbital only after the lower orbitals are filled, right? So for example, if you have 4 electrons to distribute between the 1s orbital and the 2s orbital, the first 2 electrons will go into the lower energy orbital, which is the 1s orbital. And then the next 2 electrons will go into the next higher orbital, which would be the 2s orbital, all right? So that's another thing that you have to take into account when you're trying to decide how to distribute the electrons among the orbitals. The third guideline is that for atoms beyond hydrogen, the energy order of the orbitals would be the s, followed by the p, followed by the d, and followed by the f for a given value of n. Now remember, the n represents the energy level. So what this is saying is that for any energy level where these orbitals or sublevels exist, the s sublevel will be the lowest energy, followed by the p sublevel, followed by the d sublevel, and then followed by the f sublevel, all right? That's the order of the energies of the different sublevels that exist within a particular energy level, all right? The fourth guideline that we have to follow is that if you have more than one orbital in the same sublevel, the way you distribute the electrons among these sublevels is that you assign the electrons singly to each orbital first, and then if you have any more electrons to add, you start pairing them up. So for example, let's say you have these 3 p orbitals which are in the same sublevel, and let's say you have some electrons to assign to these p orbitals. Well, the first electron will go here, right? And then the next electron will go into any one of these 2p sublevels. So the next electron will go into this one. And then if you have another electron to add, then that electron will go into the pz sublevel, right? So that's what this particular rule is saying. If you have a set of orbitals belonging to the same sublevel, then basically you spread the electrons among these sublevels first. And then if you have any more electrons to add, then you start pairing them up. So the fourth electron will go into any one of these three. So that's the electron here. The next electron will go into any one of these two. So it goes here. And then the next electron will go into the remaining p sublevel, which is this one right here. And you'll notice that when the electrons are paired up, and we made this point before, the electrons must be spinning in opposite directions. So that's basically how you assign the electrons to a set of orbitals that belongs to the same sublevels. All right. Okay. I think I'm going to stop. Hold on, let me see here. Okay, I'm going to stop here for today. All right, because what we're going to get into, as I said before, is how do we assign the electrons to the different sublevels. All right. So that's it for today. Unless there are any questions that you guys have. Let me get out of this. Okay, so are there any questions that you guys have concerning what we just covered? Or if you have any questions about the test, I've posted the test online. I think the deadline is Wednesday. So I'm assuming that there's no issues with that as far as that is concerned. Just remember, when you're finished with it, make sure that you scan it as a PDF document and upload it into the portal in Canvas. And make sure that you complete it in ink in your own handwriting. So I'm not accepting any typewritten work. And what else? Okay, let me see here. In order to only get 2 graded, do you have to do, wait a minute. So hold on, let me check something here because I didn't realize that. Let me see here. Let me see here. Let me see here. Test. Okay, let me see. I may have made an error. Now that I see that question being asked. Oh, well, you need to do all questions. Somebody asked, okay, let me go back to the question that somebody asked. Somebody asked, in order to only get 2 graded, do you have to do all 3 questions? Well, let me see here. Oh, okay, I forgot to delete this here. Actually, I'll be grading all questions. So that's why I need to answer all the questions provided. Yeah, I'm sorry about that, but yeah, I'll be grading all the questions. I forgot to delete this part of the instruction right here. So I apologize for that, but you should do all the questions anyway, all right? So that's an answer to the question that Ms. Gomez is asking. I hope that clarifies things for you. Okay, now Mr. Pinsky is saying, I don't have anything concerning today or the test, but I'm more concerned about the multiple assignments we have to complete by Friday. I'm not sure if I can complete all of them by then and balance the rest of my workload. Okay, well, I understand that. Just complete as many as you can by that day and then do the rest afterwards. I'm just gonna basically look out to see how everybody's doing and, you know, extend the deadline based on that for other assignments, all right? So yes, I'm willing to work with you guys. I know that things are a bit challenging now, you know, with what's going on and so on. So I'm willing to be flexible in terms of deadlines for those assignments. Okay, any other questions? Any other questions concerning the assignments, the test, or what we have just discussed? Let me just say that as far as the current topic that we're dealing with in this chapter, I totally understand if you find it a bit challenging because it's very abstract. I remember when I was a student, you know, I had difficulty understanding it as well, but I'm here to help. So if in reviewing the material, if you have any questions, feel free to, you know, contact me via Skype, and I'm more than willing to help you further your understanding and help you to appreciate what's going on. All right. Okay. Any other questions? Okay, if there are no other questions, that's basically it for today. So I'll see you guys on Wednesday. All right, so take care and enjoy the rest of your day.